Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, in today's lesson, 7.1.5, creating integer coefficients, we are going to begin to learn about a strategy that's a legal mathematical algebraic move we can use whenever fractions or decimal numbers appear in our equations. And a lot of people don't like working with fractions and decimals, and I understand that. Now, the decimal numbers aren't too bad because you can use your calculator, and the fractions can be relatively easy to solve if you've got only like one final step to do, like multiplying both sides times the reciprocal. But often we've got far more complicated equations and we have to work through the fractions and decimals, and it can be a nightmare. So we are going to learn some strategies that we could use to change our fractions or decimal numbers into whole numbers and integers. And we can then, once we've got them as whole numbers or integers, then we can solve them a lot more easily. So let's get to it and see what we have in store for us for this lesson. Often, one of the best ways to deal with a challenging task is to find a way to make it easier. For example, lifting a heavy weight can be made a lot easier if you use a lever or a pulley. Mathematical problems are very similar. Often, a challenging problem can be changed to create a new problem that is a lot easier to solve. So, in this lesson, you're going to develop strategies for rewriting more complicated equations into equivalent equations that look a lot easier to solve. And I say they look a lot easier to solve because essentially you're doing the same steps. It's just in a slightly different order that is more pleasing to the eye, that makes it seem like it's easier to solve. But when you really get down to it, you're really doing the same steps that you would normally do if you had never learned this strategy that we're going to get into starting today. All right, so here is kind of a complicated word problem, but I'm going to work you through it, so you just copy me down. Oop, did I forget to do something? Hold on for a second. All right, sometimes I forget to, let me actually do a little save thing happening there. Okay. So the Community Service Club at North Middle School is planning to paint apartments at the local senior citizen center next week. The club needs your help to determine how many apartments they should be able to paint in a single day. Earlier in the year, when only 4/7 of the students worked, they painted 9 apartments in one day. Okay, so 4/7 of the total, let's just presume that there were like 7 total people available, and 4/7 would be 4 out of the 7. So when only 4 people showed up, we were able to get 9 apartments done that day. So what we're trying to figure out is how many apartments would they be able to paint if all 7 people showed up. So we're going to have X in this situation represent the number of apartments that can be painted by all of the students in the club if all 7 of them were there, okay? And we're also going to assume something, and this is very, very important and unfortunately is never true. We're going to pretend like every student contributes equally to the work and you don't have anybody sitting around talking, wasting time while other people are doing all of the work. I won't name any names, but you know who I'm talking about. All right, so if X represents the number of apartments that can be painted by all of the students in the club, use a multiplier and your understanding of scaling to represent the situation as an equation. So 4/7 of the total gave you 9 apartments. So this would end up being the equation that would represent this situation. So the total number of apartments has to be a number that's bigger than 9 because only 4/7 of the total, 4 total people, were working. And so assuming everybody, like every person represents 1/7 of the job, right? So that was 4/7 of all the workforce times X equaled 9. So to choose a strategy to solve this equation, what does your answer represent? All right, so what I want you to do is I want you to see if you can figure out what X is. Go ahead and copy that down and use one of the strategies we talked about last week or in the previous lesson, I should say, it wasn't last week, to solve for X. See what you get for your answer, and I'll do the reveal in a second. So go ahead and pause and unpause when you're ready for the reveal. All right, so if you're not ready and you haven't paused yet, please pause now. This is the original equation. 4/7 of the total number of apartments were done because you had 4 out of the 7 people working, and they got 9 of them done. So I'm going to choose to multiply both sides times the reciprocal of 4 sevenths. 7 fourths times 4 sevenths gives you 28 over 28, which gives you 1x. But you have to also multiply 9 times 7 fourths, and that gives you 63 over 4, because 9 times 7 is in the numerator, and there's a ninja 1 there times the 4 in the denominator. So we need to simplify that fraction, and 63 divided by 4 can be written in fractional form, or technically could be written in decimal form. But if we took the calculator, you'd get the decimal version. 63 divided by 4 is 15.75. So 75 hundredths is the same as 3/4. So 4 goes into 60 15 times, and then that remaining 3 is your 3/4. So when we declare our answer, if all 7 students are working, they can paint 15 3/4 or 3/4 apartments in one day. This might be one where someone says, oh, I'm going to round that to 15. And you would be right if the question was asking how many total apartments would they be able to start and finish painting. Then the answer would be 15. They would still have 3/4 of an apartment that they could paint before they stopped for the day. But then the next day, they would pick up and finish that one before moving on to the next apartment. So I think it's appropriate to say 15 3/4 apartments per day is their rate of completion. All right, so Janice, the club's president, began to think about how she could visualize 4 sevenths to help her solve her equation. She recalled using algebra tiles to represent x. Remember how a long, skinny rectangle that was the color blue was the x tile? In her mind, she visualized this diagram at the right. And notice that she has visualized. You couldn't actually do this with the algebra tiles, which is why they're not great for when we get fraction and decimal coefficients. But if you could visualize it, this would represent 4 sevenths of an x. And that is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So does this equation represent the equation from before? Yeah, it absolutely does. 4 sevenths of x is equal to 9. So Janice recognized that these numbers were not easy to work with since she did not have any whole tiles to work with. After working on her paper for a while, she said, maybe I can make more whole tiles using more, or maybe I can make whole tiles using more than one set of partial tiles. So she did this. What is happening there? Before, she had this. She had one of those and one of those. But now she's got 1, 2, 3, 4, 5, 6, 7. So she has, I don't know what the word is. It's not doubling or tripling, septupling. Is that what it's called? When you multiply something times 7? She has multiplied both sides of this equation times 7. And that is absolutely an illegal move, because whatever she did to one side, she did the exact same thing to the other. So this is an equivalent visual representation to that. Now, why would she multiply it times 7? This is kind of interesting. Take a look at this. Remember how if this entire row was actually filled in with tiles, that would represent 1x? Well, let's look at it in this direction instead. Instead of putting them this way, what if we put all 7 of them this way? So that right there represents 1x. This is a second x. This is a third x. And this is a fourth x. And here you've got a total of 9 times 3 is a total of 63. So after multiplying both sides of this equation times 7, you get 4x's is now equal to 63. Which one looks easier? Solving 4 sevenths of x is equal to 9, or solving 4x is equal to 63? I think this one appears easier because all you have to do is divide each side by 4 and you will get your answer. With your team or class, or just thinking on your own because you're watching a video, think about Janice's strategy for solving this equation. What made Janice's strategy different than what you did in lesson 7.1.4? Remember, 7.1.4 was the one where we multiplied both sides times the same thing, but we multiplied times the reciprocal of our coefficient. In this case, we didn't multiply both sides times the reciprocal. What did we multiply both sides by? We multiplied times 7. And by doing that, she created whole x's. Okay? So how many sets of 4/7 of x did Janice use to get a whole number of tiles? That was 7 sets. So by multiplying both sides times 7, she created, well, hold on for a second. She did this, I guess. She created 7 sets of 4/7, which resulted in 4 sets of x's. I guess that's the way to think about this. Okay. So why did the right-hand side of the of the equation change? Well, because she had to multiply both sides by 7, which would keep everything balanced. So how does the number of sets Janice used relate to the equation you wrote in part A? Well, it's the same as the denominator. So that's the key for rewriting these equations to make them easier. You look at whatever the denominator is. If you multiply both sides of the equation times that denominator, 7 on this side and 7 on this side, that's going to cancel out your denominator, because you're going to end up with 28/7, which is the same as 4, right? So essentially, we're just canceling out the 7s and keeping the 4 times the x. But on this side, you get your 63. So that is going to be a strategy that we're going to use. We're going to look at our coefficients. We're going to identify the denominators, and we're going to choose to multiply both sides of the equation times that number, that's the denominator, and that will effectively cancel out the denominator and get us a new equation that is equivalent to the first one, to the original. So let's try it here. Will the strategy of turning fractions into integers from problem 52 work with other equations such as 2/3 of x is equal to 8? So please copy down 2/3 of x is equal to 8. Okay. And it says how many sets of 2/3 would make a whole number of x tiles? What is your denominator? Oops. Yeah, I guess we can use that. What is your denominator in this situation? The answer is, if you multiply and use 3 sets of it, that is like multiplying each side times 3. So if we multiply 2/3 times 3, you're going to get 2 for an answer, and that becomes 2x. But you also have to multiply the 8 times the 3, so you get 2x's now is equal to 24. And if 2x's are equal to 24, what does 1x have to be equal to? It has to be equal to 12. So the answer to this problem, 2/3 of x is equal to 8, x has to be equal to 12. So let's check it and make sure that is actually true. If we take 2/3 of 12, then we are multiplying 2 times the 12, and 3 ends up being multiplied times a little ninja 1 down there, so that becomes 24/3. And what is 24/3? It's the same as 8. So we know that the answer is correct. 2/3 of 12 is equal to 8, so x has to be equal to 12. All right, now let's think of it in terms of decimal numbers. Janice wondered if the method of creating a whole number x term would work with decimals. Suppose an item was marked at 15% off and the sale cost was $36.31. She wrote this equation right here. Why do you think she wrote the equation? What is she trying to find? Is she trying to find the amount of the discount, or is she trying to find the sale price? Actually, she's not doing either, right? She's trying to find what the total or the original cost was. So she wrote 85 hundredths times x, where x represents the original total price, because 85% corresponds to the sale price. 15% corresponds to the discount. So she wrote 0.85 because we're finding 85% of the total, because we have the sale price. We have not been given the discount. If we'd been given the discount, we would choose 0.15 to multiply times x to find out what the original total was. So in this situation, if you want to just use your calculator, you can. There's no problem dividing each side by 85 hundredths on your calculator and just seeing what the answer is. But if you don't have a calculator handy, there is something else that you can do. If I wanted to turn this number into a whole number, let's say the number 85, what would you multiply times this to move that decimal 2 places to the right? If you said 100, you would be correct. Go ahead and multiply both sides of this equation times 100, and you will get an equivalent equation of 85x is equal to 3,621. Now, does it really matter if you're using your calculator? No, it does not. But if you don't have your calculator handy and you're going to go use the division process and lining up the decimals is a problem for you, then go ahead and do this first, and then you can do the division and not have to worry so much about that decimal number until you get to this point right there. So divide each side by 85. What do we get for our final answer? We get 42.6. So that means that the original price must have been $42.60. Now, let's see if that is correct. If I take and I multiply $42.60 times 0.85, that's going to be 85% of the total, which would be the sale price, means our sale price was $36.21. That is correct. If the question then said, what was the amount of the discount? You could either take 42.60 and subtract away 36.31, or you could take 42.60 and multiply it times your multiplier 0.15, and that will tell you that the discount was $6.39. All right, so let's do this again, but now let's do it with two different problems. Let's take this problem right here and solve it, and let's take this problem right here and solve it by using this method here. The key is to look and see how many decimal places does this need to move to the right. If it only needs to move one place, then you can multiply times 10. If it needed to move 2 places, you should multiply times 100. If it needs to move 3 places, what do you think you're going to have to multiply by? Go ahead and see if you can figure that out. Go ahead and pause, work out those two equations, see if you get the same answer I will reveal in a moment. All right, so it says, does this method work for all equations? What if you wanted to solve these two problems? The answer is yes, it'll always work, but you may need to choose a different power of 10. Here you multiply times 10, there times 100, there times 1,000. So if you take the first problem, you multiply both sides times 10, you're going to get 12x is equal to 140. And I never really did solve the problem, so I'll do it right now. Take my calculator, and you can take 140 divided by 12, and you get 11.6 repeated. So in this case, your answer is going to be x equals 11.6 repeated, or 11 2/3. That would be the same thing as that number. For this one, we're going to take and multiply everything times 1,000, so we end up with 999x is equal to 71,200, and so we'll divide 71,200 by 999, and we get 71.271,271,271. Isn't that lovely? 71.271 with that repeating, and I don't even know what the fraction is for that. So we'll just leave it how it is. Did I get that right? 71 point, yeah. Isn't that interesting? There's a pattern there when you divide by all nines in your answer. Kind of interesting repeating pattern. All right, so here we go. Let's go ahead, copy down these 4 equations, and let's solve them using this method and see how you like it. This is officially what we're referring to as fraction busters. But we're doing it at its most minimal level where we only have one term over here that we have to work with. In tomorrow's lesson, or lesson 7.1.6, we're going to have multiple fractions that we're going to have to deal with. And that's really where the fraction busters becomes the most helpful. Okay, so go ahead, take some time, work through these, and I will reveal once you unpause. All right, let's see how you did. In this one, our denominator is a 6, so we would start by multiplying both sides times 6, and you end up with 5x is equal to 24. Then you take 24 divided by 5, and you get 4 4/5, which also can be shown as, stop it. Why do you do that? Drive me crazy. Which could also be shown as 4.8. In this case, I would multiply both sides times 10, since there's only one decimal that you need to move that over. So this becomes 8x is equal to 190. And then 190 divided by 8 is 23.75. which I suppose could be 23 and 3/4, but since it started as a decimal number, let's just keep it in decimal form. For this problem, 3 is our denominator. So if we multiply both sides times 3, we end up with 5x is equal to 12 times 3, which is 36. Now, I didn't quite say it over here, but I will show this real quickly. Remember, when you multiply times 3, we're just canceling out the denominator. That's why we're choosing to multiply times whatever the denominator is, because it'll automatically cancel it out and just leave you with the numerator times your variable. It always works that way. So 36 divided by 5x, or divided by 5, I should say, gives you 7 1/5, which, if you did it on your calculator, would be 7.2. And then in this case, you got 2 decimals you need to move that over, so we should multiply times 100. So that becomes 12x is equal to 100. Then you take 100 divided by 12, and you get 8.3 repeated. And of course, it's a good idea to check your answers. So let's see here. If we took 5/6 times, and these are hard to check. Oh, goodness gracious. All right, this is how we'd have to do it. But use your calculator to help you along the way. 5/6, let's put it into decimal form. 5 divided by 6 gives you this decimal number. When you multiply that decimal number times 4.8, you should get 4 for an answer, and we do. So that one checks out. This one, we're going to take 0.8 times 23.75. Does that give you 19? Yes, it does. That's what we wanted. In this situation, we have to take 5 divided by 3 to convert that to a decimal, then multiply it times 7.2. That should give us 12 for an answer. Yes, it does. And in this case, we're going to take 8.3 repeated, 8.3 repeated, and just keep pushing that button as long as we possibly can. Then multiply that times 0.12, and that should give us 1 for an answer, and it does. So everything checks out. We are good to go. We have got our answers for X. And that ends the process, which is the beginning of your understanding of how Fraction Buster works. So let's go do your homework and maybe a check for understanding. Not quite sure what's coming up next. And then tomorrow, we'll get deeper into the concept of Fraction Busters. All right, take care. Bye.
Hey, feeling good, like I should.